I'm Martin Wallace.
I'm Darren McCarthy.
And I'm Dan Fury.
And this is The Fundamentals.
What's our subject this week?
We're talking light.
Light.
Now that sounds like a pretty broad topic, which it is.
It is.
I think it originated with the idea of talking about LEDs.
Oh, for us, yeah.
Light emitting diodes.
Yep.
And then we thought, well, there's a lot more going on than that.
Mm-hmm.
Where does it all come from?
Let's boil it down.
Yes, we really can't talk about LEDs, and we will talk about LEDs
I
tonight.
hope so.
We can't talk about LEDs without talking light first.
Yeah, all kinds of
Yeah.
light. All kinds of light bulbs.
Mhm.
Where does...
I brought an example today.
Did ya?
Yeah, of a light bulb. And we'll get into that later. That's a lot of fun. That's the hands-on science that I let other people do, and then I just turn on. And then we look at it.
Yeah, we see it.
Yeah.
Feel it.
Light is an astoundingly broad topic and an unbelievably complex one. And we're going to get into things that are going to be totally hypothetical tonight. And we're going to talk about concrete things as if we know what we're talking about, when in reality, we don't.
We don't.
But the good news is we brought in an expert in the field, and
We did.
I'd like
Yeah.
to let him introduce himself.
My name is Wes McComb. I live in Charleston, South Carolina, and I teach physics for the Navy.
And that would be where his introduction is going to go.
I'm pretty sure this is how Radio Lab does it.
Oh, yeah.
Yeah.
It's the hand motions.
Quick cuts.
Mhm.
And this...
So,
Thanks, Wes.
Thanks, buddy. We'll be back to you soon.
yeah. Thanks for being live with us in the studio. Wes McComb, everybody.
And the live studio audience goes crazy.
You like Wes, don't you? We do too.
So, what is light?
What the heck?
Now, I think, like most people, when I hear the word light, or if I'm asked to describe light, I'm talking about the visible spectrum of
We're
light.
talking about visible light.
Yeah, so
Light you can see.
light that I can see, or that humans can see, or what we experience as light kind of in our reality. That is a tiny fraction of a very broad spectrum of what light scientifically would be considered, which is electromagnetic radiation.
So the basis of our perception of light would be the sun's light, wouldn't it?
Yes, but we are only seeing
Oh, I'm sure.
part of the
Right.
light that is
Thankfully.
actually coming from the sun. So we're experiencing light between a certain set of nanometers, which is very, very small. And
Unbelievably small.
Nano.
these are wavelengths of light, of energy, of radiation, electromagnetic radiation coming from the sun. So we're seeing between 400 and 700 nanometers within those wavelengths. Now, if you lower the wavelength, you're going to raise the frequency. And if you up the wavelength, you lower the frequency. So now we're talking about
Think about like waves in a pool.
yeah,
The larger the wave and the wider the wave, the larger the distance between the crests of the wave, the less waves are going to happen per cycle.
Mhm.
But if the distance between the crests of the wave are shorter, so many more happen per cycle. And that's exactly what's happening with light on a scale that ranges from the size of buildings to the size of atoms. And even bigger than building size of, there's theories that the universe, there's a wavelength the size of the universe.
You know, this is something that I thought about. When we talked about gravity, we talked about certain insects that they're so small, like their scale is so small that walking up a wall or across the surface of water, you know, that's their reality, that it's possible to walk across water, where we don't experience that. And we had talked about that about
Jesus spider?
yeah, like that, this Jesus spider scientists would never consider gravity the same way that we do.
Yeah.
Because it's not a part of their reality. And we had a conversation about what do you think is beyond our even perception. And I feel like that kind of comes in with this. So something like a radio wave is electromagnetic radiation.
It's light,
It's light.
Yeah.
Same
but it's
thing.
not light that we can see.
Yeah. And the wavelength is about the size of like a building compared to gamma rays or like gamma radiation, which is
Size of atoms.
the size of atoms.
Now we have to take
So small.
a quick detour here because now we're going to talk about atoms. And when we talk about atoms, we get into a microscopic world so unbelievably tiny. We need a little anecdotal story here for them. So every atom is made from 3 kinds of elementary particles. This is some basic chemistry here for you. Protons, which have a positive electrical charge, electrons, which have a negative electrical charge, and neutrons, which have no charge. Protons and neutrons are packed into the nucleus, while electrons spin around the outside. And you've seen graphs of this that look like solar systems. And that's not true at all. But the problem is this is on such a scale that we have no real way of understanding the reality that these things exist in. And that is because the nucleus of an atom, where the proton and the neutron are, is so tiny. So if you were to expand it to our dimensions, the atom would be the size of a fly inside of a giant cathedral, or it would be the size of a marble inside of an NFL stadium. And the electron is zooming around it in the stands. And these are the smallest things that we know about, right? So we're in this unbelievably tiny field that also has this incredible amount of distance in between it. And so this zooming around that the electron's doing is more like a wave than it is anything else, from the best way that I've come to understand it in the past week, is that instead of thinking about it as a planet spinning around its sun, it's more like a wave oscillating in this space around this incredibly dense, tiny little package that is undefinably small. And that's where all of this energy is coming from. Light is affecting these things, and gamma rays are this tiny. And at the same time, the size of buildings.
Something I think about whenever, because I've heard that analogy before too, of the scale of an atom. So so like a marble or a baseball or whatever, like in the middle of a football stadium. And then the electron being, the scale of it is being like a fly following the periphery of the stadium. And I was thinking about, it's like if you were standing in the middle of that stadium, if you say you had like some super hearing or some device that you could hear really sensitive vibrations in the air, like sound waves, you would hear that fly, but there's no way you can know where it is.
Oh, yeah.
But you know it's there.
It's like everywhere at once and at the same time in a precise spot, but you're just following it around.
Yeah. So it's like you're never actually, all you know is that you are in the middle of this giant stadium and there's a fly.
Well, sometimes you're just in a small room.
Think
and
about
you hear
that.
a fly.
Yeah.
And where the fuck is the fly?
And you can't find it. Yeah.
It's everywhere at once and at the same time has a precise location, but you don't
know where it is. It has an effect on you too,
Yeah.
because then now you're like, it's there. It's affecting you.
Where is
in
it?
the center?
So this is the scale of things that we're working with when we talk about electromagnetic radiation. So I was curious that word gets thrown around a lot when you say light, and people say, oh, it's electromagnetic radiation. And I'm curious, what does that mean?
Right.
It doesn't mean anything to you. It doesn't mean anything. It's just another way of saying, well, this is
it's
B
just a term.
and B is A. It's light is EMR. EMR is light. But what we're talking about is light is a form of energy at its most basic. It's a wave, and it travels in waves similar to waves of water in the ocean. But with light, the waving is not the water. It's electric and magnetic fields that are tied together. So light is a little bundle of these fields that are intertwined called electromagnetic radiation that propagate themselves in photons. And that's about as far as I've gotten. It's crazy. So it's the fastest thing in the universe.
Mm-hmm. It's a constant.
It's a constant speed.
In a vacuum, which we'll get into when we get to refraction and rainbows, basically.
Yay.
So what Martin just said about the magnetic field and the magnetic in the electromagnetic field. So like on an oscillating scope where you have like the wave kind of shape.
Actually, I gotta say, when you guys are talking about cycles and stuff like this, I immediately think of it like audio.
Yeah.
and reading waveforms because I do that so much, especially
Sure.
with this.
So that's a good visual. It's a different mechanic
Sure.
interaction though. So with
But
sound,
there's cycles and there's different modes of
And
cycles.
when you talk about like hertzes and stuff, it's
Yeah,
the same like system to describe, just a different event.
And there's also like a much farther spectrum of audio that you can't hear.
Yeah.
sure.
Humans can hear like 20 hertz to
Exactly. It's the same thing with the visible spectrum. There's a limit to what we can hear and there's a limit to what we can see, but that is by no means the limit to what exists.
yeah.
right.
And it really comes down to like the cones and rods in our eyes, or the photoreceptors in our eyes, just aren't. They didn't evolve to see,
pick up anything.
pick up any of those wavelengths. And there are other animals, other species on Earth, like some insects that don't rely on a lens for their vision. Just the physical structure of the way that they see is picking up different wavelengths. But because the light that enters into our eye is focused by a lens, it's going down to a specific spot. It's being picked up by rods and cones.
Yeah.
To see certain wavelengths. And that's, I mean, I think from the evolution side of things, probably like these are the wavelengths that we needed
Right.
for what we were trying to get done,
Yeah.
200,000 years ago. But you look at something like a pit viper that, they say like snakes, they can see the infrared.
Right.
So they have this other sensor, basically, that is picking up those wavelengths of light. And so it's not like an eye, like the way that we experience vision, but it's just a sensing organ that's picking up those wavelengths of light.
Yeah, it's not right to say that when we pick up the infrared on our infrared cameras, that's what these animals see.
Right.
It is more like they are just sensing it in their own particular way, which is why you can't say that everything with eyes is seeing things the same way. Even us as humans, which nearly identical sensing equipment, is picking everything up in its own way and being interpreted in its own way. But when, it's like what dogs smell.
Yeah.
They might be able to smell a whole lot more than we do, but what they're smelling and how they're interpreting that is all beyond our comprehension.
Well, I think that's something that it fleshes out the image of the world around them. And the same thing with like marine mammals. They'll have these sensing or sense receptors in their jaw, like thousands of them, that effectively act the way that our ears act. So they're picking up sound vibrations. So it's instead of having 2 ears, they have thousands of ears, but it's not in the same sense of an ear. They're picking up the vibrations of sound in a completely different way, but it's also fleshing out the world around them the way that I think that we rely quite a bit on the optic nerve.
Oh, yeah.
And in reality, we're picking up next to nothing on the spectrum of what we can see, whereas other animals have gone other ways.
So the electromagnetic spectrum goes in descending order of wavelength to increased frequency of radio waves, microwaves, infrared radiation, visible light, the ultraviolet, X-rays, and then gamma rays. I think we're all familiar. We've heard all those terms before. Ultraviolet, of course, is what tans your skin. Infrared's what you see in those awesome little cameras that pick up the heat from your body and that kind of stuff. We use microwaves. You're familiar with X-rays.
Oh,
we use
sure.
the radio all the time. Gamma rays I've never used a gamma ray piece of technology to my knowledge.
Yeah, I don't think you would.
They sound dangerous. They sound the most dangerous.
Yeah, I think that if you have that level of radiation, the way I remember it being described is like if you think of like the cells in your body as being people, a gamma ray is like a freight train.
Mm-hmm.
So it's just coming through and it just destroys.
Yeah,
cells.
at the ultraviolet things start to get messed with your cellular level.
Yeah,
And then X-rays, of course, are dangerous at a high exposure, but gamma rays,
I think they're pretty
it's
dangerous.
just cancer.
Maybe we should talk about the photon side of things
Okay.
and the wave particle duality.
Wave particle duality is fun.
Let's get into that.
It's exactly like it sounds, that light can be explained has a wave and has a particle depending on which angle you're looking at it, your view of things. So if you try to look at it at a specific moment, it acts like a particle. And if you try to look at it otherwise, it propagates itself as a wave.
Mm-hmm.
And this is way, way more complicated than that.
Yeah. Is this involved in metaphysics somehow?
It's more in like quantum mechanics.
Okay. Yeah, that's what I meant.
So, for example, a single photon, which is the quanta of light, which quantum mechanics, quanta is the smallest part of what you're looking at, right? Best, easiest way I can describe it, it's the most minuscule amount of a thing is its quanta, which is why in quantum mechanics you're talking about the most minute scale of things. So a single photon, which imagine light itself is almost its energy to us is practically
central
not noticed
to so much. Yeah.
But it's such a tiny amount of energy. We get hot from the heat from the sun, but that's a huge furnace.
Yeah.
But when you talk about like individual pieces of that light, it's so minute. And so a photon is just tiny. And a single photon may be refracted by a lens or exhibit wave interference with itself, but may also have a definite position when it's measured. So it has all of these properties that can't be explained by it being either a wave or a particle. It has to be both. And that makes it incredibly difficult to measure in a lab.
So photons they're essentially a massless particle. So it's like a packet of energy, which my brain can't handle.
No, it's too small.
Yeah. But this also means that it has these long distance interactions. So seeing the light from a star that's probably dead at this point, those are massless photons of light energy reaching all the way to us from, 1,500 light years away.
Right.
In like one continuous stream of that, it's constantly being refreshed.
Yeah.
You continually see the star. So when you look at the sun, you're looking at one long beam of its light energy traveling to you continuously.
This is such a complicated episode.
It's tough. Yeah. It's really tough. A really cool property of light is that it has momentum to it. And you've never felt in your life the pressure of that.
No.
Like you've never been pushed by light. But at a microscopic level, it's happening. Light carries momentum with it. And this has some practical applications. There's like microscopic, that's a really funny name. Let me find it.
Are those really all your notes for this episode?
Yeah.
Wow.
Nano electromechanical systems, or NEMS, which is applications that are at nanometer scales. And a nanometer is 10 to the negative ninth or a billionth of a meter. Unbelievably small applications and like computer systems and stuff, where you could use the effects of light pressure to flip switches in nanometer circuits instantaneously to essentially create any kind of application you need on such a microscopic level.
And wouldn't it be heat free, right? If there's no mass, there's no friction.
It's just the force of the photons hitting a switch.
That's crazy.
That would turn a thing on. And to put this into perspective, you could lift a penny with laser pointers, right?
Mm-hmm.
If you were to point 30 billion of them at a penny, you could push a penny around.
What?
But at this nanometer scale, you can use light to flip switches at a speed that's faster than anything else in the universe. And that's awesome. And so far, I don't really know what they're doing with this technology, but the fact that we have that kind of technology to build things at a nanometer scale is ridiculous. So, of course, the main source of light on the Earth is the sun.
Sure.
Right?
Of course it is.
Mm-hmm.
So we have plenty of light bulbs and man-made light. We'll get into that, which is very, very important to us. But the sun does this wonderful thing called photosynthesis. And for that, we have to go through a little bit of biology. So It is the process by which plants and other microorganisms trap light energy from the sun and use it to convert carbon dioxide and water into sugar, transforms solar energy into the chemical energy required by all living things. How that works is fun and complicated. A thing called a chloroplast is the specialized organule in a plant cell where photosynthesis takes place. They're surrounded by a couple membranes, blah, 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 a thing called stroma, and we don't need to know any of this stuff. So millions of molecules of chlorophyll, which is a pigment that absorbs energy from the sun, gives leaves and other plant structures their green color. And if you've ever wondered why things are green, the answer is not photosynthesis. The answer is not because green is the prettiest color. The answer is because in photosynthesis, what is happening is the plant is essentially eating, and that's kind of a fun metaphorical way of thinking about photosynthesis. It's eating the light. And what it's doing is it's eating light on two ends of the spectrum. It's eating the shortest wavelengths, the red, the longer wavelengths, the shorter frequency, and the opposite, the violets. And what's left is what it's not eating, which is the green. So the reason why grass is green, when you look at it, is because it's not eating the green. It doesn't need it.
It's reflecting the green.
So it goes, back to you. So if it was eating the green and the violet, grass would be red.
I wish grass was red. That'd be
Well,
awesome.
it could
it is.
It
could be.
I mean,
depending on
It
how
also is.
literally depending on how you look at it.
it is red. We just don't see
Can't
it
see
that
it.
way.
That's crazy.
And that kind of goes for everything you see
Yeah.
that has color.
Except for the things that emit light. That's
Yeah.
the difference.
Yeah,
If
it's
it's
different.
emitting light itself, it is the color that you see it. But if it's reflecting light, like your shirt is all of the colors that your shirt is not, actually. So this is one of the reasons why when it's hot outside, you want to wear a white shirt. When it's cold, you want to wear the black shirt because black is absorbing all of the light, reflecting less of it. White is just the opposite, reflecting all of it back. So when you see this shirt, it is not really this grayish blue, but rather it is all of the colors that this is not.
That's what I see.
But that's what you see. It took thousands of years for that to be figured out. Thousands of years.
That's crazy.
So I watched this. This is awesome YouTube channel. I love this guy, Matthias Wandel. He's this guy up in Canada, and he's like this engineer guy. And I've been watching his videos anyway for a while now.
Yeah.
And it's always like something really weird and interesting and engineering related, you know. But for this, I thought I'm going to see what he has to say about light. So he of course had a video about this viewer had sent him a bunch of light bulbs, like LED light bulbs, and he was saying, "Hey, I noticed in your videos you're using these incandescent fluorescent light bulbs all around your shop and your house." So he sends all these LED light bulbs, and he says that these have a broader light spectrum. So the first question is like, who gives a shit? You know, like they're lights. But then, so this guy Matthias goes and takes these light bulbs and puts them into like a bunch of different fixtures, and he runs all these experiments about them. And he uses a CD, like a CD-ROM, to refract the light like coming from these. And he shows you on the CD like these two light sources coming in, and you can see the whole spectrum of what's being emitted. And then like on the fluorescent light, there are these dead zones in the spectrum. So there's like the red, the green, the blue. But then on the LED, like the full spectrum LEDs, it's like a smooth transition between all of them. And I was thinking about that, just like the mood of a light, even like at my house, putting different brands of light bulbs.
Oh yeah.
It's huge.
What I'm hoping we're going to talk about is temperature of light
Yeah.
and lumens.
Mhm.
Because there's a huge difference in temperature. What is the rating of temperature?
It's like
Starts with a K.
a Kelvin.
The Kelvin scale.
It goes like, this is really big in photography, you know, it goes up to like 10,000 Kelvin down to I think 1,000. It's
Most light bulbs are on the warmer side, like the bulb that's in this room here. It's pretty warm. It's almost a yellowish light.
Mhm.
Where you get onto the cooler side, which is much more
blue,
bright
white. Yeah.
Yeah. Cool.
And of course, it's very dependent on how the light bulb works.
and what the source is, like if it's incandescent, if it's LED,
Fluorescent.
if it's fluorescent.
Mm-hmm.
Here's a pretty good scale. I think that's pretty easy to visualize. So you have something like a match flame. It's rated to
Very warm.
was like 1700 Kelvin, which is kind of like the orangey side. Now we think of that as warm,
Yeah.
but that's the red side of the spectrum.
Right.
So that's a
Longer wavelength.
longer wavelength, whereas the higher Kelvin is actually the bluer side of the scale. It's a shorter wavelength,
Yeah.
but it's a higher frequency.
Mm-hmm.
So something like the clear blue sky, like which is basically sunlight.
Right. Usually a cooler temperature light bulb is associated with daylight.
Yeah, I think though that we think of blue as cool.
Yeah.
So like the higher the Kelvin though, the more blue it gets.
Yeah.
Because it's a shorter wavelength.
That's
higher
usually how
frequency.
it's marketed, though.
Yeah.
If you want a cooler, brighter white light, it's associated with daylight. 'Cause
Yeah.
I recently bought light bulbs.
I think it very much depends on what type of bulb you're buying.
It does, yeah. And I was
Because-
buying the LED lights.
Yeah,
for instance.
because they work on a totally different system. So what you're describing is incandescence, which is light from heat.
Mhm.
So light from heat is going to be acting in the way that you're describing now. The hotter it is, the closer it's going to get to the blue side of things, shorter wavelength, higher frequency. The cooler it is, the warmer it's going to be, or the more red, even though those terms are opposite. But with something like an LED, it turns out an incredibly complicated system of electrically charging a bunch of electrons and having some holes in a thing in which they fill. And I don't understand it at all. Would probably be more true to the color that you're buying and more have something to do with those kinds of adjectives.
So do we have an explanation for what an LED light is?
No, I tried.
It's a light emitting diode.
It's two bars that are pressed together that have holes in them. And one of them is a bunch of electrons that are negatively charged, and then the other side has a bunch of positive charges in it, and you run an electrical current through them. And when you do, they attract each other and try to fit each other into the holes. And how that emits light and the color that it emits, I have no idea.
Basically, it's passing photons, I think, back and forth.
Yeah, good luck.
Sure.
It's
I understand incandescence, and was the other one, of course, is fluorescence.
Of course.
Fluorescence is actually pretty difficult itself.
Yeah.
You know how fluorescence works?
Well, not really, no.
So we'll start with incandescence just for everybody at home.
The classic.
Incandescence is light, as you've always known it, outside of the office. It's light based off of heat. Filaments are heated to a particular temperature, and it's incredibly inefficient because, as we know,
they burn out.
they not only burn out, but most of the energy is on a spectrum in which we can't see. So although those light bulbs have worked fine forever, the amount of energy that have been pushed into them to make light,
It's a bit of a waste.
so much of it is going to emit a range of light that we can't see.
Yeah.
So that's essentially incandescence. It's the emission of electromagnetic radiation from a hot body as a result of its temperature. We all know this from Edison, of course. Fun little bit of history there outside of light for our history buffs. Historians Robert Friedel and Paul Israel have listed 22 inventors prior to Thomas Edison, but say that his version of the light bulb is what we remember because of a list of its effective incandescent material, the higher vacuum that he was able to get because of a thing called a Sprengel pump, and the high resistance that made power distribution from a centralized source economically viable. So Edison did not invent the light bulb, but he is who we remember as doing it because he was the Steve Jobs of light bulbs. He just made it better. So we remember it.
Yep.
So when anybody ever says Edison did not invent the light bulb, they're right. Fluorescence, however, is the
Correct.
emission of light by a substance that has absorbed light of other electromagnetic radiation, and the emitted light typically has a lower wavelength and therefore lower energy. So a gas takes in higher wavelengths of electromagnetic radiation and then emits visible light because of it. So you have those tubes that are filled with a gas that is being hit with ultraviolet light, and it then in turn turns it into a lower frequency of light or lower wavelength of light that we can see. That sucks.
Yeah.
Nobody likes fluorescent lights.
It sucks.
But this stuff occurs naturally, biofluorescence. You can see it in nature, and there's lights that you can see when you turn the lights off. There are parts of things, you've seen that like neon glow of minerals and artificially induced things, and it's crazy. And what that is it absorbs all of this radiation and then emits it at a lower energy level because it's just kind of pushing it back out. So I understand how those two things worked. LEDs is going to take a week in and of itself.
Yeah.
So
That's what I thought.
Yeah.
That's what I thought.
It seems though that like LEDs are the way to go.
Yeah.
Yeah,
They're like
it
the
sure
most
does.
true to
Actual light.
and lowest amount of energy.
Yeah.
Incandescents suck. Fluorescence sucks as far as the light, but
What's like the cost of like an LED light bulb though? I feel like it's probably still
Now it's getting much
Is it cheaper?
lower. Oh yeah, I just bought 3 or 4 of them, and they were cheaper, or at least the same as fluorescence or incandescent.
I might go through my house and just replace all of them.
You should.
You want to know why though? How much do you hate? You got like 4 different light sources in one room.
Mm-hmm.
If they aren't the same kind of like
It
light,
is off-putting. Yeah.
So in our
lighting's really important to your feng shui. It's
It-
just important to your life.
I think So in our kitchen living room area, we have these 2 overhead lights.
Yeah.
And I think in each light there's like 2 outlets.
Yep.
In one of them, it's 2 separate types of bulbs.
Not good.
We never turn that light on.
It's just so stupid.
you look at, and then the other one is like it's a uniform double, like the same light bulb. It's impossible. Like to eat dinner in that room.
Yeah.
Are you kidding me? To eat
Are you kidding
in
me?
those circumstances?
Oh God. Little fun piece of trivia to get back to light.
Yeah, get back to the subject.
We were talking
at
about
hand.
light.
Little fun piece of trivia. The fluorescent lamp first became available to the public at the World Fair, 1939.
Oh, shut
the
up.
same year that another product that we talked about this season, nylon. Nylon and fluorescent lamps, same year,
When did we
1939.
talk about nylon?
Plastic.
Oh.
Orson Welles, who was always dressed in nylon.
Always.
Nothing touched that body but nylon.
Mm-mm.
That was a good episode.
That was fun. Longest lasting light bulb.
LED.
This is like the current world record. What do you think is your best guess?
Of the type of light bulb? Or
It's also this right now.
Or was
what
it
about
is it an
wattage? We got to
eternal-
talk about wattage too.
It's incandescent. Just your regular old school.
Because the incandescent wattage is like the standard for how you measure fluorescent or LED. Like a 9 watt LED is
right
is a 60 watt
Yeah.
incandescent or something like that.
Because that's how much energy it takes to run
Right.
the thing.
Yeah, originally a 60 watt bulb. It's a little
Okay.
dim now.
Pretty normal though.
Think about the average like incandescent light bulb you've used. What's the once a year?
It's incandescent. Yeah, but 2-3 max.
How many years?
Could it possibly?
15?
I was gonna say like 19.
Keep going.
That's what I thought you
110?
were gonna say.
Keep going.
Wow.
Shut up.
You're really
127.
too far. 113 years.
Did they ever turn it on?
How do you verify this?
It's been turned off only a handful of times. Only a handful of times.
Is it
Where
still
in
on?
California is it?
It's in Livermore, California, maintained by the Livermore Pleasanton Fire Department. So this light was apparently donated to this is at a point in history where lights were donated. Like light bulbs were so cool, they were donated.
So cool.
In 1901
Wow.
to this fire department.
It's still
That's
on.
crazy.
It's still on. I think it's been moved around the firehouse a couple times. It's hung in at least 4 locations. Originally hung in 1901, and its unusual longevity was first noticed in 1972. So for 71 years, no one thought, "Hey, we never changed that light bulb."
That light bulb's been around here for
Yeah.
a while.
But I think it's attributed to like the bulb itself was blown glass.
Right.
It was like handmade, this light bulb.
And then the air was pumped out of it.
Probably, yeah, it's a vacuum. And then it's a thicker filament. Like it's just,
They just don't make them like they used to.
they made them to last. But I guess that this light bulb has been a argument for, all these light bulbs that burn out, it's just planned obsolescence. They want you to keep buying more.
Right. So what about fluorescent lights? Because isn't there a danger here? Isn't it the mercury a bit of a problem with these?
So,
They
yes,
last longer, sure, but there's a drawback.
an electric discharge in the tube causes mercury atoms to emit ultraviolet light, which then is eaten up and emits light that's visible to us. So mercury's bad. We all know Mad Hatter syndrome, that whole situation. But what are you going to do?
What are you going to do?
I mean, what are you
You're
going to do?
replace all those fluorescent lights with
Have you been
LEDs.
Have you been eating these lights? Have you been playing
No, but
lightsabers
if
with
they
them?
break,
Yeah.
if you breathe that stuff in, that's not...
You need to ingest a high amount of mercury,
How high?
more than
More than you're going to have time.
I don't think it's that big of a deal. It's also a big enough deal as like between that and the hellish, awful illumination that it makes. We're not gonna make that the new world standard.
I really feel like fluorescent lights are really on the way out right now.
I think
They're on the way
too.
out, but they're still way more power efficient than incandescent lights. So until we switch fully to something like LEDs, which I still don't understand, so I can't say why we haven't done that.
Could not tell you.
I'll tell you why. We had when we first moved into our house,
Mm-hmm.
this like handyman guy, he put a fluorescent light in our garage. That shit burned out in 2 weeks.
I've had fluorescent lights in my bathroom. I've replaced them
That's
twice
terrible.
in the last 2.5 years.
I think so. This
3 of them.
This is what I think happens here. So fluorescent lights they're great if you leave them on all the time.
Because it takes a while for them to really
They have to
reach
warm
their
up.
potential.
And if you're turning them on and off, you just like burn out the ballast of the light.
Yeah.
I went to a big box store and bought an LED strip light. It's awesome.
Awesome.
LEDs is the way to go.
So, and it's guaranteed to last like 40 years or something.
Whoa.
I'm all about LEDs. I don't know.
I'm all about that stuff, man. It's in
that
our
fluorescent shit.
televisions now.
But you make me nervous
It's in
now
our cell phones.
because I just put that fluorescent light just like against the wall in my garage.
Take it out.
Gonna have to get rid of that.
Take it out.
Got some mercury going.
Let's talk about refraction again for a minute.
Yeah,
I would
we-
love to. I think I've said before, refraction is one of my favorite words of all time.
I think we should dive into refraction. I think that there are 50 other tangents we could go on.
Yeah.
I
Well,
think
of course.
refraction's the
In
one.
classic fundamental stuff.
Mhm.
Dan, stop taking my lines.
Now,
I was waiting for it.
I was
simply put,
Dan, I was building up.
it.
You cut all this out. I'm going to say it in a minute.
Edit point.
simply put, refraction is the bending of light rays when passing through a surface between one transparent material and another, as in through air and water.
Mm-hmm.
Now, it's also why we have rainbows.
Yeah.
And I'd like to ask Wes
Love
McComb
rainbows.
to elaborate a little bit more for us.
Wes?
So rainbows are really best described using this wave nature, because if you ever stood in a pool and you look down, you notice that your legs are a little bit bent. That's because the light coming in from the air that you observe of your body is being bent as it enters the water. So we're calling it's being refracted. When light enters a material with a different density, usually it's going to have a different speed of propagation. This causes it to bend at that initial point it enters. Now, in classical optics, so at a more simplified treatment of it, we just treat light as this continuous bending or this single bend, and then we're all good. But if you actually get down to it, is each frequency of light, because generally when we see light come from the sun, it's a whole mixture of frequencies, a whole mixture of colors, i.e., white light is a mixture of all those colors. They all get bent at slightly different angles. And so we may have observed this when you look at a prism, where you have a nice beam of white light, a mixture of light coming in through a prism crystal. It will actually be refracted. It will be bent out into its whole spectrum of colors. So remember that I said that around down at the 400, 300 nanometers, we have violet light, kind of the higher frequency, blues and violets. Up at the 700 nanometers, we have red lights. And so that we have that OAG-BIV, red, orange, yellow, green, blue, indigo, violet. Those are all corresponding to different frequencies. Now, this effect is going to happen the same thing when you have a bunch of water droplets in the sky. So right after a rainstorm, you'll have a fair amount of humidity and a concentration of water, which makes nice little spherical drops in the air. Light will enter this nice white light from the sun, a mixture of lights, and it will undergo this refraction, separating out this light. And then because these are nice spherical drops, they're going to make this nice bow shape as they get refracted out. So really a rainbow is actually a circular shape. And it's just we only receive really half of it. The half is below the horizon, or depending upon how you look at it, can appear other ways. But it's really just up to this effect of refraction, where light of different wavelengths moves at slightly different speeds in a different material, and it will be separated out.
Dan, cut Wes out now. So that was Wes on rainbows.
Thanks, Wes.
And he's right.
He's so right.
As always. I forget what Wes just said, so let's talk some more about...
Remind me again?
You want to talk about refraction?
A little bit more.
You mean when a beam of light crosses the boundary between a vacuum and another medium, between two different media? The wavelength of the light changes, but the frequency remains constant.
This is fun stuff. So as we talked about, light is... At this point, we're talking about light as a wave. So you have this constant stream of light.
Yeah.
Or the source of light. And when it hits this medium, so it's going the sun. Okay, so light coming through the atmosphere and then hitting water molecules. Light is traveling at different frequencies in the same wavelength, and it's splitting and bending according to that wavelength. Okay. So that's where we see the white light coming from the sun that we experience as visible light being split into its individual parts.
In a prism.
In a prism is the same thing. It's putting a light
Isaac Newton again. That piece of that awesome scientist keeps showing back up.
Yeah. If anyone out there still has a CD-ROM at their house, the same idea. Just take the CD and just kind of bend it.
Oh yeah.
In front of a light.
What?
You're seeing
all those colors.
Just a music CD.
Any music CD, anything. If you have, get your favorite REM record out.
Mm-hmm.
Favorite REM CD, and just
so many,
just all their hits, and
the greatest hit CD of REM.
Those you can see all these different colors in that. That is the spectrum of light from whatever light source is hitting it. You can make rainbows.
Now, an experiment you can do with just that is to discover for yourself definitively that light is more than our visible spectrum. Because you can take that same exact split of the wavelengths, bend it, and discover that on one end it's cooler and on one end it's hotter beyond what we're able to see of the split.
Yeah.
So if you ever have to go back in time to before Isaac Newton's era, and you get yourself in a conversation with somebody about how there's more than just what you can see visibly in light, you can split light with a prism and measure the temperature above and below the visible spectrum and blow some minds. And that's how you do science at home.
That's how you do science.
That's
Also-
actually how we know what we know today is that exact experiment done.
There's something else. So this also comes into effect just with the red and blue shift of objects. So getting kind of, we've talked about in gravity, I think we talked about just interplanetary interactions of gravity or traveling through space. This same wavelength, we use this, I think, in sound waves too. It's the red shift and blue shift. So like blue shift is something coming towards you. Wavelengths, or the frequency is really high, the wavelengths are really short.
It's called compressing.
It's compressed because it's whatever's emitting that is coming at you. So it's like catching up to its own emission. Whereas if it's moving away, it's like you are kind of chasing it. But it's
In sound, what it is when a car or a motorcycle, something loud, passes you as a stationary person, and it goes, "Vroom."
Yeah.
And it's the wavelength and frequency of the sound wave is the same, but as it gets closer to you, it seems to be getting louder. And as it goes away, it's getting quieter because of this exact compression situation. It's going, "Vroom," even though it's the same wave.
And that's a way to think about like the blue spectrum, like the blue side of the visible light spectrum, is as it's coming towards you, as light's coming towards you, it's moving at a higher frequency. It's getting closer and closer and closer. The wavelength is very, very short. And so when you look at like a rainbow, that's why it's staggered. So it's like it's that light, that wavelength is really short and it's moving super fast. And it's just kind of like bending really sharp. Whereas like the red spectrum is like a longer wavelength. It's kind of going like around us or around whatever it's refracted through. And that's why it's kind of gradiated, the light. So it's just different wavelengths of the same electromagnetic radiation coming at us.
And color is really nothing more than our sensory input ability to differentiate between incredibly specific frequencies.
Yeah.
Minute, tiny changes in frequency is the enormous amount of color range that we can see, up to 1 million different colors. Last thing I looked at was we can differentiate between these 1 million different little shades of color. And when you're looking at the visible spectrum, it is a tiny amount of what light actually is. And that's what you see. These little changes in frequencies being shot at you at an incredible speed, which I don't think we mentioned yet. The speed of light.
I don't think we talked about
We've
that.
gotten this far. We haven't talked about the
It's a
speed of
little
light. Light would go around it would circumnavigate the equator 7.5 times a second.
Yeah, that's fast.
It goes 3 times 10 to the 8 meters per second. That's really specifically 299,792,458 meters a second, if you really want to get precise. And we're getting so precise, in fact, that the length of the meter is now defined from this constant, just like the length of a second is defined back to GPS,
Yeah.
if you remember.
Oh, we do.
So it's fast. So fast, in fact, that nothing can go faster.
Yeah. So now this speed of light, though, is a universal constant. In fact, in equations, it's represented by just a capital C for constant.
Most constant thing.
But that's only in a vacuum. So in the vacuum of space where there's no medium that's passing through, it's moving in that space. And that's where we get refraction of light. Just when it hits some sort of medium, it slows down, which is, like on the scale of things, it's not slow. It's
Right.
just 0.0000001%.
When there's a change in that speed, there's a describable effect.
where it starts splitting apart the
Mhm.
light.
Yeah.
And that's kind of a huge part of why we're human beings and we see with eyeballs.
Exactly. We have evolved to perceive the most dominant part of the sun's emission, and that is the most useful thing to us. And that is why our whole perception of the world visibly is the way that it is. Because we have devices now to see our infrareds and our ultraviolets and our microwaves and our x-rays and our radio waves and all this other stuff. But physically, like as organic beings, it's like we said back with the snake, with the viper. They might be experiencing the world in this infrared range of things, but it's not like our infrared cameras experience the infrared. We have just been built or evolved to pick up this not only unbelievably precise range of frequency, but what just so happens to be the most emitted frequency of the sun.
It's the most useful frequency for biological bodies like ours to find food and survive. Like, it's like the pit viper that sees the heat signature of a mouse. It's a cold-blooded animal that needs to eat. I mean, not that often, but it is super useful.
Yeah.
If you're just looking for one meal every now and then.
It just needs this one
Just,
thing.
I need some heat. What's alive? Gonna get it. And then I'm not
There it
gonna
is. Gonna get it.
And then I'm just going to sleep for a
gonna
while.
sleep for a while.
I'm going to sleep this off. Then
So
I'm going to go get another one.
It evolved that capacity to pick up that spectrum of electromagnetic radiation. We evolved to pick up. I mean, if there were food sources that were available to us that could only be picked up by seeing radio waves, we would have done so.
I would like to move on to photic. So there's a lot of vocabulary here. Photic sneeze reflex.
Yeah. Please do that.
Now, this is when you're going to sneeze and you're supposed to look at a light?
It's when you look at a light and you sneeze.
Okay.
Yeah.
Now, this
Like the
phenomenon,
sun.
yeah, we've heard this before. People you possibly have walked from
certainly.
a dim place to a bright place of view, Darren. And
I've never done that.
You've never done this.
I'm the
me
light
and
of the
you
world.
have.
Shut up.
Me and Dan have both sneezed
For
walking.
sure.
Now, listeners, this affects 18 to 35% of the population.
That's it?
Yeah, it seems more common to me because it happens all the time. I
Yeah.
walk from a dark room to a bright room and I sneeze.
Wait, all right. So this does
it's
not
that
happen.
common for me.
This has
but-
not happened to me.
Ever?
Most affected by sunlight.
It's
in my
called sun
experience.
sneezing.
Yeah.
Or photic sneeze reflex. Or the best thing ever, autosomal, dominant, compelling, helio-ophthalmic outburst syndrome.
Whoa.
You know the acronym for that?
No.
You were listening. Do you get it?
No.
It's a chew.
Fucking
Seriously,
assholes.
some scientists in some room put that together and said, huh?
Wow.
That's hilarious. Autosomal, dominant, compelling, helio-ophthalmic outburst syndrome, a chew. It's photic sneeze reflex. This has been documented for centuries. Aristotle was one of the first to contemplate, and this is just in writing that
He was
we
one of the
have,
first to contemplate a lot of stuff.
this strange phenomenon. In 350 BC, he was trying to figure out why looking at the sun causes a person to sneeze in his book, The Book of Problems. Asking, why
love
does
that
the
guy.
heat of the sun provoke sneezing? So he hypothesized that heat caused sweating in the nose, which triggered a sneeze in order to remove the moisture. He was a
Okay.
smart guy.
Yeah, logic.
Yeah. Now, in the 17th century, one philosopher, Francis Bacon, who philosophers know about, disproved Aristotle's theory, which must have been awesome to him because,
Yeah.
like, if you ever just been like, well, Aristotle's an idiot.
We've mentioned Aristotle a bunch on this.
Yeah, he keeps showing up, him and Newton and
Yeah.
Einstein and
All
now
the sciencey
Francis
things.
Bacon.
I have a serious question.
Yeah.
Is Francis Bacon in any way?
No.
He has to be.
No way.
He must be.
No, Bacon's a pretty common term.
In the sense that we all are.
Yeah.
6 degrees.
By 6 degrees of,
Yeah.
at the most.
So Francis Bacon disproved Aristotle's theory by looking at the sun with his eyes closed. Now, if Aristotle's theory was correct that the heat from the sun caused sweating in the nose, then looking at the sun with your eyes closed has nothing to do with it. So he said, Aristotle, you're wrong. I'm not saying I'm right. I'm just saying you're wrong. So he said that the eyes played a vital part in the triggering of the sneezing. So he said that looking at the sun's light made the eyes water, and that moisture proceeded to seep into the nose and irritate it, causing a sneeze. So he simultaneously proved Aristotle wrong and made a big idiot out of himself.
What a dummy.
Right. So this theory made sense, and scientists later determined it to be incorrect due to the fact that sun-induced sneezing occurs too quickly after sunlight exposure. Watering of the eyes is a slower process, so is sweating in the nose, so it could not play a vital part in triggering the reflex. So scientific attention today has mainly focused on a hypothesis proposed in 1964 by Henry Everett, who was the first to call light-induced sneezing the photic sneeze effect. So since the nervous system transmits signals at an extremely fast pace, Dr. Everett hypothesized that the syndrome was linked to the nervous system and was perhaps caused by the confusion of nerve signals. So the genetic basis of photic sneezing still remains unclear. No one has any idea why it's happening. And single genes for this condition have not been found and studied, even though it only affects a small third, almost a fourth of the population. The condition often occurs within families, though. So there's hope that we'll find a gene. And on a side note, I would like you both to know that there is a thing called sexually induced sneezing.
What?
And I looked it up, and it's awesome. And it has nothing to do with light, of course. And it has everything to do with being sexually aroused and sneezing too much. And it's awesome. That is totally a thing that happens to people.
Like getting a boner and just sneezing uncontrollably?
It's about as common as sun sneezing, which means the two of us could easily have it. And when you get sexually aroused, you just start sneezing uncontrollably. And could you imagine? I mean, you're just not supposed to reproduce.
Wait a minute, though. Isn't sneeze like a sneeze is like the second most pleasurable physical?
It feels pretty good to me.
It is oddly pleasurable.
If you're sneezing uncontrollably and you're having sex,
maybe it's like compounding.
And your partner's okay with the outburst of sneezing?
Maybe she thinks it's
Could you imagine sneezing through the whole thing, though?
Well, I can.
It's not just one or two. It's compulsively sneezing.
Yeah, I feel like
that's not something I've ever heard.
I feel like
now, if you both are affected by it, that is awesome.
I feel like there's a way to get that involved. You know,
you got to work it in there somehow.
Yeah, you could figure it out.
Sure.
Yeah,
I'm doing this for us,
babe.
And if I could, I'd like to end.
You could.
I'd like to end with saying that, as uneducated as we are about light, we did a pretty good job.
You know what? I agree.
I
really did.
I think that
go out and try yourself, huh? You think you can do better?
Yeah. I'm gonna tell you right now. We didn't even talk about black body radiation
because who knows what that means?
I don't know.
Okay, Planck, I get it. You have an equation.
We didn't talk about the chromosphere of the sun.
No,
we didn't talk about even lumens of light.
I did kind of want to talk about lumens.
It's just a dimension,
it's a measurement.
Yeah, it's just how much,
bright, how bright is essentially
it
is.
Okay. It's intensity.
Okay, simple. Got it.
The most important thing to astronomers is light. As a matter of fact, it's the only thing that we have to study interstellar bodies. And I would like to end this episode with one Wes McComb explaining that to us.
So when you're on Earth and you want to look at the sky to probe what's out there, you really have very few options. And your predominant one is observing the light that's coming from interstellar space. So people have been doing this for thousands of years. As our technology has gotten better, we've been able to look at the night sky and see the light coming in and actually break it up into its constituent parts. So when I look out there and I see a nice white or a little blue light, I can actually collect that light and get a more precise wavelength reading of that, of exactly what type of light I'm seeing. And so this is a really valuable tool for astronomers because down here on Earth, we can do certain reactions chemical reactions, maybe with hydrogen or oxygen. These electron shell changes where a electron will be excited, move up in a different orbital, and then come back down, will emit a very precise wavelength of light, a very precise frequency. And so we know what certain chemicals here on Earth, their light spectrum is going to be. And then when we look out in the sky, we can see what particular wavelengths we see, where they're peaked. And based upon that, we can get an idea of the composition of faraway stars or perhaps even atmospheres of distant planets. So when we know what a particular star or atmosphere is emitting in terms of light, we can figure out what it's composed of. For suns, this can tell us how old they are, how hot they're burning, how big they are. And that will give us a big indication about how much matter altogether is in the universe, because we can, based upon this, using our models here, determine from how these chemical reactions are actually occurring. So light is pretty much the observational astronomer's primary tool to actually see and make experimental data come out of what they observe in that.
Nailed it, Wes.
That was Wes. Man, he does a good job.
Man, he knows some stuff.
You want some lumen knowledge real quick?
Yes, please.
All right, so I'm talking about some just some general across the board equivalents here. You have your incandescent lights, your standards. Let's say like you have a 60-watt bulb.
A 60-watt Edison light bulb.
That's giving off about 800 lumens. Not very bright. You're talking about that's light in theoretically, every direction.
Mm-hmm.
So it's not even like a focused 800 lumens. So like the sun is giving off light kind of everywhere.
More light than you can imagine.
If you get into something like a polarized lens.
Polarization is the filtering of which direction of a wave that you're looking at.
Yes, the light has to hit. The light will only pass through the lens if it's traveling in a certain direction. That's where like you don't get light refracted or reflected off of something. It won't pass through like a polarized sunglass or sunglass lens. So the light has to be like lined up perfectly.
A good example of that is, say you're driving by a lake and the sun is shining into the lake and it is reflecting not only an image of the sun on the lake bed that you would see, but also that glare, that sort of just ambiguous shine of light that's annoying to your eyes. Polarized sunglasses or a polarized window shield or whatever, what that's going to do is it's only going to allow the rays of light that are bouncing towards you at a particular angle to pass through the lens. So you don't get the glare, but you get the perfect picture otherwise. You still see the sun reflected in the lake. You just don't see that odd glare on the side because your lens is polarized. It's only getting one angle into it.
A couple more lumen things here. We've been talking about LED lights. This is kind of like, I think, pretty high in the scale for most applications that we would ever have a need for commercially or like in our homes. So an incandescent light, like a 300-watt incandescent light, which that's like an outdoor floodlight. I don't even know.
Oh, what's the candle brightness of that? Like how many?
It's a 4,000 lumen light.
Wow.
That's, for an LED equivalent, would be a 40-watt draw.
Like no energy at all.
Yeah, so
less energy than the light that I turned on as the example. Which it goes back when we were talking about incandescence. Why incandescent is such a waste of energy. You made the comment that it's not very bright at all. But the fact is, when you look at it, it's hard to look straight at because it's very bright. It hurts your eyes.
I guess but
it doesn't brighten
itself.
the room.
Yeah.
It only brightens a very small amount, and that's why incandescent lights are a terrible waste of power, because it's spending so much energy in a different spectrum than visible light.
Yeah.
And all that's left over is just a heated filament that hurts your eyes to look at, but can't bright the whole room. While an LED will have more lumens than something 3 times the power of that for 20 less watts.
Mm-hmm.
All right, I'm going to go out there and say it. This was a tough episode.
Yeah.
This was tough stuff.
Yeah.
We had the help of a physics teacher.
Yeah.
I studied a lot.
I could see that.
What this boils down to is we're talking about a highly theoretical, very,
Sure.
very finicky part of existence that when we try to describe can only come out in really, really specific measurable ways, such as electromagnetic radiation, which is a very particular substance that I still don't quite understand. It's the excitation of electrons at a subatomic level doing things that are beyond comprehension, even to serious physicists.
Yeah, I think just even thinking about it as a spectrum, that the visible light that we see is the same as radio waves and gamma rays. I like that. I like that side of it. That I can kind of wrap my mind around.
Photons I get.
Photons, I get.
But not really.
No.
I mean, it's the smallest molecular level of...
a massless particle.
Mhm.
That makes no sense to me.
Its speed is beyond...
Imagining.
Here's just a fun thought experiment to leave you guys with. When you're going 60 miles an hour on the freeway and you get passed by a motorcycle who's going 70 miles an hour, you are observing the motorcycle going 10 miles an hour,
Yeah.
right? That's an easy thing to wrap your head around. You're going 0 miles an hour, you're stationary, and somebody zooms by you at 80 miles an hour, they're going 80 miles an hour. If you're going 70 miles an hour, they're going 10 miles an hour. If you're going 90, they're going
Backwards.
negative. Yeah. Everything in the universe works this way, except for light. It doesn't matter how fast you're going. Light is going light speed around you.
Mm-hmm.
And this goes back to Einstein and gravity and space-time. What changes, because that can't possibly be, is time. Time changes to account for the fact that when you're going faster, light is still going as fast.
You know, I think we got here? Classic fun.
We just got classic fundamentals. We put a thought experiment in there.
Oh,
Yeah.
boy.
It was way too broad of a subject.
Yeah.
We
We thought light was light, but it turns out light is light.
it's astronomical.
It's heavy.
I had a lot of fun, though.
Yeah.
I will say I had a lot of fun with this subject.
Good.
There's a bunch of stuff we didn't really cover, like Planck, Snell, Maxwell.
Snell's law. Yeah.
Snell's law, Maxwell's equations, Planck's constant. So, but, I mean, it's really just like, to me, it was just numbers scribbled.
Even like the law of refraction, like Snell's law. That is a wonderful thing that we know how to do as a species. We can determine the angle at which light changes through a medium
Yeah.
and what that's going to do to your visibility of it.
It's just a mathematical way of saying that, all right, so the light's coming at this angle and it's refracted at this angle. And if you drew a diagram, the angle is coming in at, and then the angle it's refracted at, there's going to be this like inverse, like a opposite but equal angle of refraction. And there's a whole equation just talking about that. But what's really cool is that we also get a measurement for each medium. So like water has a certain angle of refraction or a certain effect on light, and then something like glass or like a diamond or any sort of like just pure material would have like a different effect on the light.
So diamonds have an incredible effect on light, which is why we like them so much,
Yeah.
is because they refract a lot.
They slow light down a lot when light hits
It's
it.
incredibly pretty.
That's why this episode is forever.
I think we did the best we could.
Yeah.
It's a tough one. I hope you guys learned something. I learned a whole lot. And at the same time, I feel like I'm day one still.
Yeah.
You know, there's an unbelievable amount of math to be done.
Yeah.
Yeah. I kind of got bogged down a little bit in some of that stuff.
I kept trying to get beyond
Yeah.
the basic introduction to light, and it turned into more and more unbelievably
I'm going
complex
back
stuff.
to school.
I got to. There's a lot of fun history too that we didn't have a chance to get into, and I think would, like classic fundamentals, be separate episodes. The history of how we know what we know about light is unbelievably fascinating. It's really, really dense and really cool, and from all angles, like how we knew about electricity, we knew about magnetism, we knew about light, and how through several hundred years, all of the theories about them sort of reconciled themselves to become one theory is insane. And nobody wanted to accept it for a very long time. And how we came to figure out what the speed of light is has some of the craziest experiments I've ever read about. Galileo thought that him and a friend could stand at two different mountaintops with lanterns and wave and calculate the time in between each other seeing the waves, which of course they couldn't. And not too long after that, a giant, almost like sideways, like a horizontal windmill was constructed to shine a light onto one mirror, and as it was rotated, the light would then hit another mirror and come back. And if you could get the light to reflect outward, you could calculate based on the speed of the rotation of this thing and the distance between the light source and what it hit and came back again to. And that's how we know the speed of light, because that worked.
A windmill?
A horizontal windmill with mirrors on it. There's a whole lot to learn. I think that's why we started this in the first place.
I think you're right.
So glad we learned a little. I hope everybody listening did too. That seems like a good jumping off point for light. If you want to know the physics, it's really tough.
Yeah.
If you want to know the
Good luck.
physics, you need to go to school and then you can call us.
Yeah, but if you want to know some fun things about light, it's real fast.
Yeah. It's super fast.
So
It's
fast.
all the time.
Uh-huh.
It's more than what you can see.
It's like the fastest thing.
It's there even if you can't see it.
All right, I think we've done our work today.
Yeah.
Let's go to bed.
I'm glad it's over. That's a tough one. I'm Martin Wallace.
I'm Darren McCarthy.
And Dan Fury.